In this tutorial, I am going to find the eigenvectors of the 3 by 3 matrix, which has elements 1, -2, 0, 0, 5, 2, 0, 3, 0. By definition, every non-zero vector x which satisfies the equation A minus lambda in multiplied by the vector x is equals to the zero vector is called an eigenvector of the matrix A. What we are having there in that equation, that lambda there is an eigenvalue. So for us to find the eigenvectors, we need to find the eigenvalues first. Eigenvalues are roots of the characteristic polynomial. The characteristic polynomial is the determinant of A minus lambda in. We denote this characteristic polynomial by Pn of lambda. So what we are having there is a 3 by 3 matrix. So for this 3 by 3 matrix, our In there will be the identity 3 by 3 matrix. This matrix here, which has ones on the diagonal. This identity matrix in the formula there is being multiplied by lambda. This will result in having lambda on the diagonal. So when you subtract a matrix which has lambdas on the diagonal from the matrix A, what it will result in is subtracting lambda from elements on the diagonal of the matrix A, the 1, 5, 0. So if we subtract lambda from those elements that I've highlighted, we would have the determinant of 1 minus lambda minus 2, 0, 0, 5 minus lambda 2, 0, 3 minus lambda. So that's our characteristic polynomial there, that determinant. To evaluate that determinant, it is convenient to use the row or column with the most number of zeros. In this case, I will choose column number 1 there. So using this column, I'll look at the element in this column, the 1 minus lambda. Then consider the array of positive, negative, positive there. So I'll close the row and the column containing the 1 minus lambda, and we take note that the 1 minus lambda is sitting on a positive. So when we evaluate our determinant, we would have 1 minus lambda multiplied by the determinant of the uncovered elements. The uncovered elements, they are 5 minus lambda, 2, 3 minus lambda. So it will be multiplied by the determinant of 5 minus lambda, 2, 3 minus lambda. Now looking at this part here, this is a determinant of a 2 by 2 matrix. When we have a 2 by 2 matrix A, B, C, D, its determinant is AD minus BC. So when you simplify that highlighted part, we would have 1 minus lambda multiplied by 5 minus lambda multiplied by minus lambda minus 6. I can then go on and expand this part here, and we would have the result as minus lambda cubed plus 6 lambda squared plus lambda minus 6. Eigenvalues are roots of the characteristic polynomial. To get the eigenvalues, we set Pn of lambda to be equals to 0, and then solve for lambda. So when we set Pn of lambda equals to 0, we would have minus lambda cubed plus 6 lambda squared plus lambda minus 6 is equals to 0. I usually find it convenient to have the leading term there as being a positive, so I will multiply that whole equation by minus 1. So if I multiply by minus 1, the equation becomes lambda cubed minus 6 lambda squared minus lambda plus 6 is equals to 0. To find the roots of that polynomial there, I'll try to find factors by trial and error. If I try to substitute lambda equals to 1 into that equation, we would have 0 equals to 0, which is valid there. So what we'll be having is lambda minus 1 is a factor of that equation there. So if it is a factor, then we would have to find the other factors using long division. So using long division, I'll write the factor that we are saying, lambda minus 1. Then the polynomial there, I'll put it under the division sign, lambda cubed minus 6 lambda squared minus lambda plus 6. The leading term there is a lambda cubed divided by lambda, then we have lambda squared. Multiply the lambda squared by lambda minus 1, and we have lambda cubed minus lambda squared. subtract from the above there, lambda cubed minus lambda cubed, it gives us a 0. Minus 6 lambda squared minus lambda squared, it gives us minus 5 lambda squared. Then the other parts I write them as they are, minus lambda plus 6. And the leading term now there is a minus 5 lambda squared. And divided by lambda, then we have minus 5 lambda. Multiply the minus 5 lambda by lambda minus 1, and we have minus 5 lambda squared plus 5 lambda. Subtract from above, then we have minus 5 lambda squared minus 5 lambda squared, it's a 0. Minus lambda minus 5 lambda, it gives us minus 6 lambda, then the plus 6. The leading term there is minus 6 lambda divided by lambda, then we have minus 6. Then the minus 6 multiplied by lambda minus 1, it gives us minus 6 lambda plus 6. When you subtract, we get a 0. So what we have above there is the other factor, lambda squared minus 5 lambda minus 6. Our equation will therefore become lambda minus 1 multiplied by lambda squared minus 5 lambda minus 6 is equals to 0. Now looking at that equation, we would have two different options there. Either lambda minus 1 is equals to 0, or lambda squared minus 5 lambda minus 6 is equals to 0. From the equation which is saying lambda minus 1 equals to 0, it gives us lambda is equals to 1. Now looking at this part here, you can try to factorize. Try to find two numbers. When you multiply them, they give us a minus 6. When you add them, they give us a minus 5. Those numbers are minus 6 and 1. So we can factorize that part to lambda minus 6 multiplied by lambda plus 1 is equals to 0, which would then give us lambda is equals to 6 and lambda is equals to minus 1. So what we'll be having there is for the 3 by 3 matrix A, and the eigenvalues are lambda 1 is equals to 6, lambda 2 is equals to 1, lambda 3 is equals to minus 1. What I did there is I wrote the eigenvalues starting with the largest one. So we have those are 3 eigenvalues. And for each of the eigenvalues, we are going to find an eigenvector using the equation that we mentioned earlier, A minus lambda in multiplied by the vector x is equals to the 0 vector. So I write that equation, A minus lambda in multiplied by the vector x is equals to the 0 vector. Substitute the matrix A that we have there, a 3 by 3 matrix, then put the lambda. The identity matrix is the identity 3 by 3 matrix. Our vector x is a column vector with 3 components, x1, x2, x3. Then the right hand side is the 0 vector with 3 components, 0, 0, 0. So we have that equation, and we now go on and look at lambda equals to 6. So for lambda equals to 6, we are substituting 6 here where we have this lambda. And when I substitute 6 there, we would have that matrix A minus 6 multiplied by the identity matrix multiplied by the vector x is equal to the 0 vector. Then I can go on and simplify that, because when you multiply that 6 by the identity matrix, we would have 6 is on the diagonal, and you'll be subtracting from the matrix A. So what it will result in is subtracting 6 from elements on the diagonal of the matrix A. So it will be 1 minus 6, which gives us a minus 5, 5 minus 6, which gives us a minus 1, then 0 minus 6, which gives us a minus 6. So that equation simplifies to minus 5 minus 2, 0, 0 minus 1, 2, 0, 3 minus 6 multiplied by the vector x is equals to the 0 vector. Now when we are doing matrix multiplication, it's a row by column. So the first row there, minus 5 minus 2, 0, by that column vector, it will give us minus 5x1 minus 2x2 plus 0x3 is equals to 0. For the second row, it would have 0x1 minus x2 plus 2x3 is equals to 0. For the third row, we would have 0x1 plus 3x2 minus 6x3 is equals to 0. So we have those 3 equations, and I'll label them equation number 1, equation number 2, and equation number 3. But if you look at equation number 1 there, what we will see is that minus 5x1 minus 2x2 is equals to 0. And then I'll go on and try and write x2 in terms of x1. What I always try to do is to write the other variables, the x2, x3 in terms of x1. So def x2 is equals to minus 5 over 2 x1. And I'll call that equation number 4. We then go on and substitute equation number 4 into equation number 2. Both, if you look here, we are having minus x2. But we are saying x2 is minus 5 over 2x1. So when we put minus 5 over 2x1 on that highlighted part, we will have 5 over 2x1 plus 2x3 is equals to 0. And then go on and write x3 now in terms of the variable x1. And then we would have x3 is equals to minus 5 over 4 x1. So we are having those two equations. X2 is equals to minus 5 over 2x1. X3 is equals to minus 5 over 4 x1. Our vector x, we say it is a column vector which has the elements x1, x2, x3. So substitute the x2 and the x3 which are above there, and we would have our vector is x1 minus 5 over 2x1 minus 5 over 4 x1. We then go on and set x1 to be equals to alpha, where alpha is a real number. This stage will allow us to factor the alpha from that vector. Because as it is, we cannot factor a variable x1. We can only factor constants. But if we set it equal to alpha, then we can factor out an alpha. So if we set x1 equals to alpha, then our vector becomes alpha minus 5 over 2 alpha minus 5 over 4 alpha. Alpha we are saying is a constant. We can factor it out there. So we have alpha 1 minus 5 over 2 minus 5 over 4. So that's the vector that we are having there. But alpha is a real number. So what you'll be having there is infinitely many eigenvectors. But all these vectors are a scalar multiple of this vector here. So what we'll be having there is the linearly independent eigenvector corresponding to lambda equals to 6 is the vector 1 minus 5 over 2 minus 5 over 4. So that will be the linearly independent eigenvector. All the other vectors are a scalar multiple of this vector. But we may try to write our vector to have components which are whole numbers. So we can rewrite this vector with components which are whole numbers. So I can multiply throughout there by 4. And we would have 4 minus 10 minus 5. So we would have our linearly independent eigenvector there is 4 minus 10 minus 5. So that's the linearly independent eigenvector corresponding to lambda equals to 6. We now move on to the second eigenvalue, the lambda equals to 1. So we are substituting 1 here where we have that lambda, and we would have the matrix A minus 1 multiplied by the identity matrix multiplied by the column vector X is equals to the 0 vector. So what it will result in is subtracting 1 from the elements on the diagonal of the matrix A there. And when you subtract 1 from the elements on the diagonal, the result will be 0 minus 2, 0, 0, 4, 2, 0, 3 minus 1 multiplied by the vector x is equals to the 0 vector. By matrix multiplication, row by column, for the first row, it will give us 0x1 minus 2x2 plus 0x3 is equals to 0. The second row will give us 0x1 plus 4x2 plus 2x3 is equals to 0. The third row would give us 0x1 plus 3x2 minus x3 is equals to 0. Here, those three equations, I'll go on and label them equation number 5, equation number 6, equation number 7. Now looking at equation number 5 there, we'll be having minus 2x2 is equals to 0, which will then simplify to x2 is equals to 0. So I'll call that equation number 8. Then substitute equation number 8 into equation number 6. So we are looking at here where we have the x2. We are saying the x2 is 0. And it will give us 2x3 is equals to 0. which would then give us x3 is equals to 0. So we are having two equations there. X2 is equals to 0, x3 is equals to 0. There is no equation which is limiting x1. So our x1 will just be x1. It's not limited to anything. So our vector x is x1, x2, x3. But we are saying x2 is 0, x3 is 0. So our vector will be x1, 0, 0. We then go on and set x1 equals to alpha, where alpha is a real number, and we would have our vector becoming alpha 0, 0. Alpha is a real number, so we can factor it out there, and we would have alpha multiplied by the vector 1, 0, 0. What we'll be having there is infinitely many eigenvectors, but these vectors are a scalar multiple of this vector here. So what we'll be having there is the linearly independent eigenvector corresponding to lambda equals to 1 is 1, 0, 0. So I'll go on and write it on the left there. The linearly independent eigenvector corresponding to lambda equals to 1 is 1, 0, 0. Now move on to the third one there, for lambda equals to minus 1. Substitute minus 1 here. So when you substitute minus 1, it will result in a plus there. So we'd have the matrix A plus the identity matrix multiplied by the column vector X is equals to the 0 vector. So what it will result in there is adding 1 on elements which are on the diagonal of the matrix A. So if we add 1 on the elements on the diagonal of the matrix A, we would have 2 minus 2, 0, 0, 6, 2, 0, 3, 1 multiplied by the vector X is equals to the 0 vector. By matrix multiplication, we would have the elements there, row by column. For the first row, we would have 2x1 minus 2x2 plus 0x3 is equals to 0. For the second row, we would have 0x1 plus 6x2 plus 2x3 is equals to 0. For the third row, we would have 0x1 plus 3x2 plus x3 is equals to 0. So we have those three equations, and I'll call them equation number 9, equation number 10, and equation number 11. From equation number 9 there, we'll be having 2x1 minus 2x2 is equals to 0, because the other part is 0. So we'll be having 2x1 is equals to 2x2. And write x2 in terms of x1, then we'll have x2 is equals to x1. So I'll call that equation number 12. And then substitute equation number 12 into equation number 10. Both in equation number 12, we're having an x2 there, but we're saying the x2 is x1. So if we put x1 there, then we'll have 6x1 plus 2x3 is equals to 0, which would then give us x3 in terms of x1. Would have x3 is equals to minus 3x1. So what we are having there is those two equations, x2 is equals to x1, x3 is equals to minus 3x1. Our vector x has components x1, x2, x3. But we are saying x2 is x1, x3 is equals to minus 3x1. So our vector becomes x1, x1 minus 3x1. Let us go on and set x1 equals to alpha, where alpha is a real number. Our vector then becomes alpha, alpha minus 3 alpha. Alpha is a real number, therefore we can factor it out there. Then we have alpha multiplied by 1, 1 minus 3. That vector there, 1, 1 minus 3. So what we are having there is infinitely many eigenvectors. But all these vectors are a scalar multiple of this vector here, 1, 1 minus 3. So what we'll be having there is the linearly independent eigenvector corresponding to lambda equals to minus 1 is 1, 1 minus 3. So I'll go on and write them there. So what we are having there is for the matrix A, which has elements 1, minus 2, 0, 0, 5, 2, 0, 3, 0. It has eigenvalues lambda equals to 6, lambda equals to 1, lambda equals to minus 1. And the linearly independent eigenvectors are 4, minus 10, 5, 1, 0, and 1, 1, minus 3. So those are the eigenvectors over that matrix.